have Kalen Patton today talking to us about clique partitions of random graphs. Take it away, Kalen.
Hi, thanks. So I'm going to be talking about clique partitions of random graphs. And this is part of joint work that I did with He Guo and Dr. Lutz Warnke. And in fact, I think He Guo, after this talk, is going to talk about another result from this same body of work. But for now, I'm going to talk about clique partitions. So, okay, oops, sorry. So first, if you're unfamiliar with random graphs, the random graphs that we're going to be looking at are the so-called Erdős-Rényi graph, GNP. So this is the graph on n vertices, in which each of the n choose 2 possible edges we insert independently at random with probability p. And studying properties of GNP is usually a good way to get insight into sort of typical graph behavior for parameters that maybe are difficult to study in general, because, with high probability results on GNP can then translate into statements about almost all graphs. So in particular, we're going to be mainly considered with the case where p is constant and then look at the behavior as n goes to infinity. And I also wanted to state a few sort of well-known properties of GNP that happen to be relevant to our discussion. First of all, the number of edges in GNP, it should come as no surprise, is approximately n choose 2 times p, since edges are binomially distributed. So we have on the order of n squared edges. And also the size of the largest clique is perhaps a little less obvious, but this is going to be closely concentrated around 2 log base 1 over p of n. So on the order of log n for the clique number of GNP. Okay, and then the graph parameter that we're going to be looking at analyzing is this so-called clique partition number. So a clique partition of a graph is a collection of cliques in the graph that sort of partition the edge set. So in particular, we want a collection of cliques that cover every edge, but then also ensure that the cliques themselves are edge disjoint. So we can see an example of this down here at the bottom. If you look at the graph on the left, one way we can sort of come up with a clique partition is in the middle. If we take this clique of size 4 and then take all the remaining edges as 8 cliques of size 2, that gives us a clique partition of size 9. And then perhaps another way that might be a little more efficient, we could also take these 4 triangles as cliques of size 3, and then take the remaining 2 edges as cliques of size 2 and get a clique partition of size 6. And so in general, we're going to be looking at how to find or how to determine what maybe the size of the smallest clique partition of G is. And we're going to call that the clique partition number. And one thing that I kind of want to note from this example down here at the bottom is that in general, it's not always obvious how to find the smallest clique partition. One heuristic you might guess is maybe we want to pick cliques of large size because, if we pick cliques of large size, then we cover more edges than a single clique. But this kind of can show how if we pick the largest cliques, we may end up actually getting a less optimal clique partition. Okay, so the question that we're going to look at is, can we study how this clique partition number behaves on the Erdős-Rényi graph GNP? And so this can sort of give us some insight into how this parameter behaves in general. So the first thing that we can do is we can establish a simple lower bound on the clique partition number of GNP. So if we kind of were to assume an optimal case where maybe all of the edges in GNP were contained in these edge disjoint cliques of maximum size, then the number of cliques in a clique partition would be the number of edges in GNP divided by the number of edges in a maximum size clique. So then we have this expression here, number of edges in GNP over the clique number of GNP choose 2, which, because we know how both of these properties behave in general, gives us a lower bound on the order of n squared over log n squared. So that helps us get a lower bound, but then the problem with finding an upper bound is a bit more challenging. So we know in general from Hall that any graph on n vertices has clique partition number at most n squared over 4. And we also have a prior result from Fries and Reed that shows that with high probability, there is a clique cover of GNP with size on the order of n squared over log n squared. Clique cover is similar to a clique partition, except we relax the requirement that the cliques be edge disjoint. So in clique cover, they can overlap. But this result doesn't immediately generalize to the clique partition case because it may be the case that many of these cliques have substantial overlaps. So that brings us to our main result, which is that we can, in fact, sort of naturally extend this theorem by Friese and Reed to the clique partition case. So for any constant p, we can find constant c1 and c2 so that the clique partition number of GNP is bounded above and below by these multiples of n squared over log n squared. And so what this sort of tells us is that the edges in GNP are contained in these large cliques, well, large being on the size of, or on the order of log n. Yeah, so all edges are contained in these order log n cliques that are edge disjoint, or mostly order log n cliques that are edge disjoint. And it also tells us that the smallest clique cover and smallest clique partition of GNP are usually roughly the same size, the same order of magnitude, which is not always the case in general. In general, you can find graphs that have significantly different clique cover and clique partition number. Okay, and so now I want to get into sort of how we establish this result. So we've already seen the lower bound. The lower bound comes from this kind of easy argument, but the upper bound is a little more challenging because we sort of have to actually give a way to find this small clique partition. And we do this by coming up with this random algorithm that is going to iteratively select cliques from our graph to include in our clique partition. So the way our algorithm works, as I said before, it's an iterative algorithm. And so we're going to iteratively define this decreasing sequence of subgraphs starting with GNP. And we define this sequence of subgraphs by, at each step, we select some large cliques from the graph GI to remove. And when I say remove, I mean removing the edges. The vertex set is going to stay the same throughout. So we select a few large cliques to remove, and then we add these cliques to our clique partition, and the graph that we get after removing their edges becomes the next clique in our sequence, or sorry, the next graph in our sequence. And the idea is that if we do this enough times, we keep removing edges from the graph and adding cliques to our clique partition, that ultimately we should eventually get a graph G big I, which is so sparse that we can just take all the remaining edges as cliques of size 2 and add them to our partition. Okay, and then the key property that sort of allows us how to analyze how many cliques that we get in each step in order to guarantee that our clique partition is small is that if we carefully select how we choose these cliques, we can guarantee that each of these intermediate graphs GI roughly resembles an Erdős-Rényi graph GNPI for some exponentially decreasing sequence of edge probabilities. And when I say resembles, I mean resembles in terms of its clique structure. So it has a similar number of cliques, and each set of vertices contains a similar number of cliques to the random graph. And so because this sequence of edge probabilities is exponentially decreasing, we can sort of guarantee that most of the cliques that we select come from the first few steps of the algorithm, which means that they are cliques of large size in GNP, which is what we want. Okay, and now to kind of show how we can maintain this key property throughout the algorithm, I wanted to give a rough overview of sort of one step. So in one step, we start from a graph GI, which resembles an Erdős-Rényi graph GNPI. And the first thing we do is we sample a random set of Ki cliques. So Ki being some fixed fraction of the clique number of GNP, so largest clique. So here you can see we're working with not really cliques of maximum size, but cliques of some fixed fraction of the maximum size. Okay, and the next thing we want to do is sort of handle any collisions that arise. So in the first step, we may get cliques that overlap. And so in order to guarantee that our cliques that are edge disjoint, we take any pair of overlapping cliques and we select one to break down into its component edges, which we consider as cliques of size 2. So you can see here in this sort of example on the right, if we have these two overlapping cliques of size 4, we convert one of them into its component edges and then remove any edges that would cause a conflict. So this guarantees that all of our cliques are edge disjoint. And then the last thing that we do is we sample a set of stabilizing edges. And this is what helps us ensure our sort of inductive hypothesis that each graph resembles an Erdős-Rényi graph. And the idea behind this step is that, we want to guarantee that each edge sort of has the same probability of persisting from one step of the algorithm to the next. And that's what gives us sort of these pseudo-random properties of resembling error training graphs. But you might notice that in the early steps of the algorithm, if an edge is contained in a lot of ki clicks, it has a much higher chance of being removed. And if it's only contained in a few ki clicks, then it has a much lower chance of being removed because there are fewer clicks that may be selected to remove it from the graph. So in order to stabilize these probabilities, we also add an additional probability of being selected to each edge as a click of size 2. And so that guarantees that we get this, all clicks have the same probability of persisting, so we can sort of use that as a basis to argue that each graph resembles an error training graph. Okay, and then the last step of the algorithm, of course, is we remove the edges of these selected clicks and add the clicks to our click partition. And one thing I also want to mention is that, so we get these sort of 3 different classes of clicks that we add, these blue, red, and green clicks. And it happens that the blue clicks make up the predominant majority of the clicks in our partition. The green and the red clicks they sort of contribute negligibly. And so that guarantees that most of the clicks used in our algorithm are these large clicks. Okay, so that basically is a rough overview of what the algorithm that we use and how it gives us a small click partition. And next, I just wanted to state some sort of extensions that we have of this result. So for instance, we can say, we looked mainly at constant p, but our argument also holds true if we allow p to vary with n in some range. So this theorem here is just saying that if we allow p to vary between n to the -2 and some 1 minus gamma for some constant gamma, then our algorithm still gives asymptotically matching upper and lower bounds. One thing that I might note here, though, is that this 1 minus gamma is actually something that we really need. We don't really know what happens in the case where p is allowed to go to 1 with n. In fact, our lower bound also breaks down in this case, because we can find a sort of better lower bound using a slightly more sophisticated argument than the trivial lower bound we got earlier. And so because of that, that means that this sort of hypothesis that maybe these bounds hold for all p is not necessarily the case. So what I'm saying here is basically the case where p goes to 1 is still open. Okay, and so to summarize sort of what we discussed here, we're looking at the problem of finding click partitions, which for general graphs is a non-trivial problem, but for the graph GNP, we find that the trivial lower bound on the click partition number can give us the correct order of magnitude for the upper bound. And we can get this upper bound by using this random click selection process. And so the remaining questions that we still have are how does this click partition number behave in the case where p is allowed to go to 1 with n? And also we might be interested in, for constant p, can we find the sort of correct constant that we get from this order of magnitude bound? So we get, upper and lower bounds up to a constant, but we still don't know exactly what maybe the correct constant is in front of that order. Okay, and so that is basically all I have for today. Thanks for listening.
All right, thank you very much, Kalen. Let's briefly thank the speaker. You want to do that? And are there any questions from the audience? So one question, perhaps just to recap my understanding of how this algorithm works. So in each round, the way you add to your clique cover is you pick a bunch of cliques that are fairly close to the largest size possible. You'll include all of them, some of them by actually being the clique, some of them by being like sub-cliques if they intersect. And then also just some kind of random edges just to make sure that these probably work out as the rounds go on, right?
Yeah, exactly.
Okay, cool. Good.
I was gonna ask if you know of any work where someone's tried this algorithm, but maybe like in a non-random context, like, just I have this graph, do something kind of like, because this seems like the kind of sort of thing that you could translate into a deterministic algorithm.
Yeah, I actually don't know of any work where this is done in a non-random setting, but yeah.
So, okay, I like to mention is that actually this result you can realize that deterministically one if you host graph satisfies some pseudo-random property.
Mm-hmm.
So
That'd be my
maybe
follow-up.
not GMP, but some graphs like the satisfy some regularity condition. That also works.
Nice. And one other small question. So you mentioned this result by Hall. Is that like a corollary of Hall's marriage theorem or just an unrelated result of Hall?
Wait, say again, what was the theorem of Hall?
So there's like the only theorem of Hall's that I like really know offhand is like Hall's marriage theorem. So I was just wondering, is this like a corollary of Hall's marriage theorem or just like an unrelated result of theirs?
I don't know. This argument comes from, or there's a result by Hall that basically says that you can cover any graph with edges and triangles, basically. And so this partition comes from that.
Okay. Any other questions for Kalen? Great. If not, let's thank the speaker again.
Thank you.